Well, thank you all for attending the webinar. And thank you, Jim, for that really interesting talk about your DLI maps. So for the past few years, the American Floral Endowment has funded research at the university that looked at supplemental lighting for ornamentals and how we can best manage that lighting. So I'll just be giving a few highlights from that research today and talk about how you will hopefully be able to use some of the work that we have done. So Jim already talked about the need for supplemental light and the fact that the daily light integral that you get from sunlight is often not enough to actually grow high quality plants or have short enough production cycles. And that's something that I'll come back later, because I think shortening production cycles may in many cases be one of the main benefits that you can get from providing supplemental light, because shorter production cycles basically mean more terms that you can get in your greenhouse, and that very quickly has a pretty big economic impact. So the maps that Jim has are great. We have been working on a slightly different kind of map that we want to use to help you estimate how much it would cost you to actually provide supplemental light in your particular greenhouse. And this work is largely being done by Cale Harbick at Cornell University, along with Neil Madsen and myself. And what this map shows is basically that if you want to maintain a daily light integral of 17 moles per day throughout the year, so every single day you would have at least 17 moles of light, how many hours a year would you need to turn on your supplemental lighting system? And that is assuming that your supplemental lighting system is pretty powerful and can provide 200 micromoles per square meter per second, something that you might typically see in a vegetable greenhouse, commonly not so much in an ornamental greenhouse. But if we make some assumptions about the cost of electricity and the amount of light that you need to provide, as well as the efficiency of your lights, we can use this map to come up with estimates of how much it will cost you on an annual basis to actually provide that supplemental light. And I just noticed that in this slide, we actually express that in hectares, the cost in hectares per year. So to convert that to acres per year, you would divide these numbers by roughly 2. But so 1,000 hours of supplemental light from a high efficiency LED light is going to cost approximately $30,000 per hectare per year. For the best high pressure sodium lights that are on the market, the electricity cost would be $44,000 per hectare per year. So that can quickly add up, but it really depends on where you are in the country, because in different parts of the country, you have to provide different amounts of supplemental light. So when we look at Athens, Georgia, for example, it would cost about $30,000 in electricity to provide that supplemental light to maintain a daily light integral of 17 moles per square meter per day. If, on the other hand, you go to Yuma, Arizona, the electrical cost would only be $6,000 because you have so much sunlight there that you really don't need supplemental light, and investing in a lighting system in Yuma is almost certainly not going to be cost effective. When we look at Seattle, Washington, the annual cost there would be about $75,000 per year. In Michigan, $65,000, and upstate New York, $55,000. So the costs really are very different in different parts of the country, which makes looking at some of the economics a really difficult problem. But it is something that is really important to think about, because when you consider the cost that is associated with providing supplemental lighting, it is often the second largest expense in a greenhouse after labor. And so managing your lighting well can really make the difference between being profitable or losing money. So when you are thinking about how to use your supplemental lighting system, you really need to try to focus on optimizing the return on investment. And unfortunately, that is a really difficult thing to do. And I'll come back to that topic later on in this presentation. But so that cost of the supplemental lighting is really high. And because of that, you have to really try to make sure that you provide supplemental lighting when plants can use that light most efficiently. So my PhD student, Jeff Weaver, has been studying how different bedding plants use light and when they use light most efficiently. So I'm going to present some of his work and talk about the implications for supplemental lighting that has. So this graph just shows 3 days of sunlight data, so the photosynthetic photon flux in November in my research greenhouse at the University of Georgia. So you can see that the light goes up and down pretty rapidly, and even during the day, you can see that sometimes during the day we can get pretty high light levels, even in October. And then shortly after that, the light levels can drop very dramatically, and part of that is related to cloudy weather, but part of it is also simply related to the fact that we have this overhead structure in the greenhouse that can shade your plants as well as the light sensor here. So as these light levels go up and down over the course of a day, it turns out that the light use efficiency of the plants also goes up and down, but it tends to move in the opposite direction. So the light blue symbols here indicate the light use efficiency of plants, and basically that refers to what fraction of light that they get can they actually use for photosynthesis and growth. And so you see that efficiency is really high at night when there is no light, so that high efficiency doesn't really help much when there is no light. And during the day, as light levels go up, the light use efficiency tends to go down. And we can look at that more clearly when we actually plot the photosynthetic photon flux against the light use efficiency, like I did in this graph right here. And this is data for petunia, and there certainly are differences among different species. But so you can see that as light levels increase from 0 to 1200 micromoles, the light use efficiency goes down from about 0.8 to as low as 0.35. So 0.35 means that only 35% of the light that a plant gets is actually used to drive photosynthesis. And ultimately, that is the reason that you are providing supplemental light. When we think about what a plant actually does with the light that it gets, it turns out that it functions in many ways really similar to a solar panel. The very first thing that happens in a plant when it gets light is that a current is created inside of that leaf. So there are literally electrical currents running through that leaf. And we can actually, from the light use efficiency and the light level, very easily calculate what that current is. And we call that the electron transport rate here. And that really is just a fancy term for the current that is generated by the light in units that happen to be the same as for the photosynthetic light, micromoles per square meter per second. So you see here that as the light level increases, we are generating more of a current inside of that leaf, and ultimately that current is going to provide the energy that a plant needs to grow. So if we just remove the data points here and just look at the overall trend, we can use graphs like this to estimate the benefits that we get from supplemental lighting. If, for example, we have no sunlight, and now we add 80 micromoles of photosynthetic light, as indicated by the yellow arrow right here, the electron transport rate increases by about 25 micromoles. If we already have 200 micromoles of sunlight and then add the same 80 micromoles of supplemental light, this white arrow again indicates the increase in electron transport rate that we get. And it's lower here than it is here. So we get less benefit from providing that supplemental light. And as we go to higher and higher levels of sunlight, you can see that the benefit that you get from adding this 80 micromoles of supplemental light becomes smaller and smaller and smaller until you have almost no benefit at all anymore under sunny conditions. So what this means is that it is really important to make sure that you provide your supplemental light when there is little sunlight present, because that is going to give you the biggest increase in electron transport rate, the biggest increase in growth, and ultimately the biggest bang for your buck from using the supplemental light. So to help growers do that, what we have done at the University of Georgia is to develop a pretty simple automated system that can actually do this. The system that we developed consists of an LED light. We have a light sensor, and both of these are connected to a controller. So this controller is getting data from the light sensor, so it knows how much sunlight is reaching the crop, and the controller can then send a signal to the LED fixture to tell the LEDs exactly how much supplemental light to provide to make sure that the crop underneath that light gets the light that it actually requires for good growth. And so this kind of an approach works with any LED lighting system that is fully dimmable. Many LED lights on the market are dimmable, but not all of them. To give you an idea of how this works, so under sunny conditions, the controller notices that there is lots of sunlight reaching the sensor. It will automatically turn the LEDs off. But when you get less sunlight, what the controller will do is send a signal to the LED light to make sure that it provides just enough supplemental light to reach a light intensity that you as a grower can specify. So what that means is that when a cloud comes in and you get less sunlight, the LEDs will immediately respond to the fact that there is less sunlight and provide enough supplemental light to make sure that your crop can still grow the way you want it to grow. So in the initial version that we developed, we could maintain the photosynthetic photon flux or the light intensity at the canopy level, as well as the photo period. We have since upgraded this system so that it can actually provide a specific daily light integral within a photo period that works well for you. Because many of the crops, of course, that we grow in greenhouses are very photo period sensitive, so you need to have control over that photo period. To give you an idea of why that actually matters, a company that I am part of, Candidus, has developed software to look at what this actually means with regard to the cost of supplemental lighting. And we can do these simulations for different locations and different times of the year throughout the entire United States. So in this example, we're taking weather data from 2004, and we assume that we have a 1-acre greenhouse where we turn the lights on at 9 a.m., we turn them off at 11 p.m., so they're on for 14 hours a day. And the graph in the bottom left right here shows the daily light integral for this particular location in Ohio over the course of this December month in 2004. Well, this green light indicates a target daily light integral of 12 moles, which is good for many ornamental plants. So you see that in December in Iowa, you're probably never going to have enough light to actually achieve the DLI that you would like. Now let's assume that you have a pretty powerful lighting system that can provide 200 micromoles of supplemental light, and you turn that those lights on for 14 hours a day, then this is the kind of daily light integrals that you would get over that same period. So pretty much every day, you reach that target daily light integral of 12 moles per square meter per day, but on many days, you provide substantially more light than what the crop really needs to grow well. And more light means that you're spending more money on electricity. So if you have a smaller lighting system that can provide 100 micromoles per square meter per day, these would be your daily light integrals, and you can see that in this particular scenario, you would not very often actually reach that DLI of 12. While if you have a system that can actually respond to sunlight in real time and is programmed to achieve a specific daily light integral, then you can pretty much hit that target daily light integral every single day, but you don't provide more light than what is needed. And when you look at the bottom row here, that shows the estimated electricity costs for these different lighting scenarios. So having 200 micromoles for 14 hours a day would cost you about $17,000 an acre for this 1 month. It would be only half of that if you provide half of that amount of light. And it would the cost would be about $12,000 per acre if you actually have a system that can achieve a specific daily light integral, but not more than that. We have done these kinds of simulations for different months. So this is for February. And in February, we see that we really overshoot the daily light integral if we provide lots of supplemental light for 14 hours a day. While with what I call an adaptive lighting approach, the only days here that we actually provide more light than what is needed for the crop is on days that there is lots of sunlight present. But we provide just enough supplemental light on all the other days to make sure that the crop gets the light it needs to grow well. And what that does is actually it reduces your lighting cost to about 1/3 of having lights that are simply controlled using a timer. And then a similar story for March 2004. And so we can very easily run these simulations for different parts of the country, different kinds of lighting systems. We can take into account the transmission of your glazing material, as well as the electricity price that you pay. So if you're interested in these kinds of simulations, let me know and we can run these for you. To actually apply that in your greenhouse, I noticed during the questions that Jim got that at least one of you actually has the e-GRO smart bar system. And so the e-GRO smart bar system has this light sensor that is built into the LED fixture and can control this LED light to make sure that by the end of the day you achieve a specific DLI, which you can program through a computer or a smartphone app. So this kind of technology is commercially available at this point, and e-GRO has tried this out at a college in California, and the data in this graph is from a sunny day in California, and even on that sunny day, they still needed to provide supplemental light to actually reach the DLI goal for the crop that they had in the greenhouse. I think this was lettuce. But so basically what you see in this graph, and I can't stop the animations, they just keep going, but the difference between the purple line and the yellow area is actually the amount of supplemental light that is provided by the lights. So early in the morning and late in the day, the lights are on, and the only light the crop gets is actually from the LEDs. But then as you get more sunlight, the LEDs will automatically provide less and less supplemental light. During the middle of the day here, there is no supplemental light provided, and the crop gets sunlight only. And so by the end of the day, you get a specific DLI, and as a grower, you can very easily set what that DLI is. My own company has developed this controller that can do very similar things to the e-GRO smart bar system, but what we are doing is to develop a system that integrates with third-party dimmable LED lights. We don't actually make our own LEDs, we make systems that can be connected to LED lights made by others. So why does DLI control matter? Well, another one of my graduate students, TC Jayalath, has done a study looking at the effects of different daily light integrals on the growth of ornamental seedlings. And we are really interested in seedling production because the value of seedlings per square foot is so high that it is relatively easy to get a good return on investment of a lighting system. And of course, we typically grow these seedlings in late winter, early spring, so that the plants can then be finished and ready for the spring gardening season. So a lot of the ornamental seedlings actually do get produced during the darkest time of the year. So supplemental lighting can make a big difference. So this is just an overview of what the research setup in the greenhouse looks like. We have these LED bars right here, which we can control precisely, and then underneath those bars, in this case, we're growing impatiens and vinca seedlings. And we had 5 different treatments, which I will explain in just a second. But we worked, as I mentioned, both with impatiens as well as vinca, and we picked these 2 crops because impatiens is a very shade-tolerant bedding plant, while vinca really likes lots and lots of light, so we wanted to have 2 contrasting species. And we harvested seedlings at 15, 20, and 30 days after they had been under these lighting treatments. They had already been in the greenhouse for 10 days before we actually started the light treatments to give the seeds a chance to germinate. So to give you an idea of how the control works, I want to show this graph that shows both the actual photosynthetic photon flux in the greenhouse, the red dashed light, and then the target photosynthetic photon flux, which the control system calculates that we need to maintain to achieve a specific daily light integral by the end of the day. So until 10 a.m., actually, the LEDs do not come on. The LEDs then can provide, when needed, supplemental light from 10 a.m. till midnight. So early in the day, the only light that we actually provide to the seedlings is sunlight. Then during the middle of the day, this control system starts to calculate the minimum amount of light that is actually required to reach the daily light integral. When the sunlight exceeds the amount of light that is required to reach the daily light integral, the LEDs will automatically be off. So during this whole period, the LEDs are off. They came on briefly here, came on again here, would be off during this sunny period in early afternoon. And then they get turned on for the rest of the day to make sure that by midnight we have achieved the daily light integral that we want to achieve. So we can do this because these LEDs are dimmable, and we can make sure that they provide just the right amount of light to get to that daily light integral. So to give you an idea of how well that system actually works, so the 3 data points that just showed up in the graph here indicate 3 of the treatments we had, where the target daily light integral was 8, 12, or 16 moles per square meter per day. This is what happened on the second day, and actually if we look at the whole 30 days of the study, this is real data. You can see that we have perfect control over the daily light integral that these seedlings get. So we had 2 other treatments in this study, one in which we provided sunlight only, and one in which we provided 100 micromoles of supplemental light for 14 hours a day. And there you can see that the daily light integral just goes up and down based on the weather conditions that we have on a specific day. So we have a lot of variability in light from day to day. To look at what that actually means for the crop, we, as I mentioned, harvested plants at 15, 20, and 30 days under the lighting treatments, and we measured shoot and root dry weight. And this graph shows shoot dry weight, so you can see without supplemental light, the seedlings grew very poorly, stayed pretty small. And it turns out that, not surprisingly, the more supplemental light we actually provide, the more shoot dry weight, or the bigger the above ground plants of the seedlings were. But when you're growing seedlings, what you're probably mainly interested in is the root dry weight. So this shows the root dry weight of these plants at the different times that we harvested. And again, what we see at the end is that the more light we provide, the more roots we have. But what I really want to draw your attention to is the difference between supplemental light and the root dry weight that we had 10 days earlier with supplemental light. So it took, without supplemental light, about 10 days longer to produce the same amount of root as it did with supplemental light. And what that means is that your production cycle is going to be a lot longer if you don't provide that supplemental light. So one of the real benefits of providing the supplemental light is not so much that you get more root dry weight, but that you can produce a saleable plug more quickly, and in turn that you can get more turns out of your greenhouse space. We also calculated a quality indicator that we call plant compactness. It is basically the dry weight divided by the height, and the higher that number is, the more compact and the higher quality the seedlings are. So once again, we see that without supplemental lighting, compactness is low. So we have seedlings that stretch for the light, that have little biomass, while with supplemental lighting, the more light we provide, the more compact the seedlings are and the higher the quality is. We collected the same data for vinca, and we basically saw the same trends for shoot dry weight, root dry weight, and compactness, where more supplemental light results in faster growth of these seedlings as well as higher quality. So overall, both the shade-adapted petunias and the sun-loving vincas showed fairly similar responses. The vincas, especially without supplemental light, actually grew very, very poorly. They didn't do well at all. So if you grow that kind of a crop, you really do need to make sure that these plants do have enough light to be able to develop a decent root system, which is ultimately going to determine the success of the transplanting. So why does it matter? So you can shorten your cropping cycles with supplemental lighting. That is true for seedlings. It is also true for finishing. If you have a system that is capable of the adaptive lighting approach that I explained, you can get consistency and predictability. If you know exactly how much light you're going to get from day to day, you can very easily predict when a crop is going to be ready. And that can be a real challenge if you don't have a lighting system that gives you consistent amount of light from one day to the other. And then the return on investment, of course, is what ultimately really matters. And it is really difficult to give recommendations on that because there are so many different factors that go into the return on investment. One of those factors is how valuable is the crop that you're growing? How long is it in the greenhouse? How well does the crop respond to supplemental lighting? And then what are the capital costs of your lighting system, as well as the installation of the lighting system, and the operating cost, which depends on how much you run your lights and your electricity. So there has been a lot of research on how to grow plants with either high pressure sodium or LED lights. There has not been a whole lot of work actually on trying to figure out the return on investment. Is it profitable for you to provide that supplemental light? So we do hope to do that. So the American Floral Endowment is funding perennial research in my lab for the next 2 years, but also thanks partly to the initial funding that we got from the American Floral Endowment, we have just started a new national research project on lighting in horticulture. We got a $5 million grant from the USDA, and UGA, Cornell, Rutgers, Rensselaer Polytechnic Institute, Utah State University, and USDA ARS will all be collaborating on this project, and we really want to focus on trying to optimize cost effectiveness or return on investment of lighting. I was hoping that by now our website would be up, so you can see the address right there. It is not up yet, hopefully next week. So if you want to follow our progress for this project, which we have nicknamed Lighting Approaches to Maximize Profits, please check that website. You can also find us on Facebook as well. And then I would like to thank the various agencies and companies that have provided support for the research that we do. And I would especially like to thank e-GRO, the American Floral Endowment, and Brian Webker for hosting today's webinar. And with that, if we have time for questions, I would be happy to.